It's exam 1, physics 102 from spring 18. The force between two charges which are separated by 2 meters is 12 newtons. If the force is now 3 newtons, what is the separation of the charges? Well, I know that F is equal to KQQ over r squared. And this force is going from 12 newtons to 3 newtons, so it's experiencing a 1 over 4 decrease. That means that the distance has to be increased by a factor of 2. So whereas it was 2 meters, now it's going to be 4 meters. Charge, certain distance from another charge, was the magnitude of the force? Well, just like we were doing before. So F is equal to KQQ over r squared. That's 9 times 10 to the 9th. That's that Coulomb's constant. Q is 4 times 10 to the minus 9 coulombs. Notice I leave the sign off. 2 times 10 to the minus 9 coulombs divided by the distance is 2 centimeters. Move that over 2 spots. 0.02 meters squared. And that gives me a value of 1.8 times 10 to the minus 4. Newtons. So a proton and electron initially separated from one another are released from rest, which will experience the greater magnitude of acceleration. Well, my proton and my electron, they experience the same force, but since F is equal to ma, the electron has a smaller mass, so it has a bigger acceleration, about 10,000 times the acceleration, because the mass is about 1/10,000th that of a proton. 3 charges are arranged as shown. Which vector best represents the net force on the bottom charge? Okay, well, my forces look like this. Due to these 2 charges, my force is in this direction. Due to these 2 charges, my force is attractive and twice that original force, so it looks like that. If the 2 forces were identical, it would be A. That is, if this vector and this vector were the same length, the answer would be A. But they're not, so the answer is B. 2 charges experience a force of 18 newtons. If the force between the 2 charges is tripled, what is the new force on the charges? Well, gosh, this is a lot what we had before. F is equal to KQQ over r squared. If I triple this, I get a factor of 1 over 9. And where it was 18 newtons, now it's going to be 1/9 of that, which is going to be equal to 2 newtons. So E is number 5. You have a configuration of 2 charges as shown. The point C is equidistant from both charges. You want to place a third charge, so the net force on that third charge is 0. What must the sign of the charge be, and where should it be placed? Well, let's just sort of play around and see where we can find. Let's say, what if I put a positive charge here? Well, it will feel attracted to that one, and then it'll be repelled from that one. So I can't put a positive charge. In fact, I can't put a positive charge anywhere here. What if I put a negative charge here? Well, it would be attracted to the +3 and repelled from the -2. So I can't put a negative charge either. So nowhere in the middle. So that gets rid of B, E, D, and I'm left with either A or C. Okay, so let's think about to the left. Actually, I'm sorry, I'm going to fix this, but this should say right of the 3 Coulomb charge. What's that, number 6? So where can I put, let's imagine, what if I put a charge over here? First, let's just imagine a positive charge. It will feel attracted to the -2 and repelled from the +3. And because it's further away from the bigger charge, there is a point over here where there is equal but opposite forces. So let's imagine now what if I had a negative charge? Well, it would feel repelled from the -2 and attracted to the +3. So I can either have a plus or minus to the left of the -2 charge, and so it's that one. But if I tried to put, say, a positive charge over here, it would be attracted to the -2 charge, but repelled from the +3, but with a bigger amount because I'm closer to the bigger charge. And so this force will be bigger always than this force. The force due to the +3 charge is going to be bigger than the force due to the -2 Coulomb charge. Okay, let's look at this. What is the electric field at point P? Okay, let's just say P. I will change that. Number 7. So I have 2 electric field vectors. I have an electric field vector, I'll call this E1, that is in that direction. and then I have an electric field vector E2 that's in that direction. And so I want to calculate what E1 and E2 should be. First, E1, the magnitude of it is kq over r squared. That's 9 times 10 to the ninth. Q is 8 times 10 to the minus 9. So leave that negative off. Divided by 4 squared. Kq over r squared. But some of these numbers cancel out. This goes away and this just becomes 2. So this is 4.5 newtons per coulomb. And then E2 divided by the distance, which is 2 meters squared. Cancel, cancel. Brings me a 2 down there. This is also 4.5. And so the answer is going to be the square root of 4.5 squared plus 4.5 squared. And let's see, let's draw these correctly. These two vectors should be the same. Oops. Should be the same. That gives me square root of 4.5 plus 4.5 gives me 6.4. So the answer is C. And then the angle here, we know that this is an equilateral right triangle, so this is 45 degrees above the negative x-axis. So B, when I'm looking for the direction. What is the potential at point A? Well, I have potential due to this charge and due to this charge. V is kq over r, so V is going to equal to 9 times 10 to the ninth. That's K. Q is minus 8 times 10 to the minus 9 divided by 4 meters plus 9 times 10 to the ninth 2 times 10 to the minus 9 coulombs divided by 2 meters. I can cancel some things. These go away. That becomes 2. I'm left with minus 18 plus 9, negative 9 volts. So the potential there is B. Notice that when I'm calculating the potential, which is a scalar quantity, I have to leave that negative in. The negative doesn't denote a sign. It sort of goes back to when we were talking about work. When the force and the displacement are in the same direction, you get positive work. When they're not, you get negative work. So it's related to that in a way, because voltage, of course, is energy per charge. So it's related to our work. Consider the previous figure where we place 3 coulomb charge at point A. What force does it experience? Well, we've already calculated the electric field, and so I'll just say F is equal to Q times E, and that is going to be, I'm going to put in a 3 coulomb charge times 6.4 newtons per coulomb. That's 19.2, or just 19 newtons. The harder way, of course, would be to actually calculate what F1 is, F2 is, and you can certainly do that, and then say the square root of F1 squared plus F2 squared, because they're on the x and y axes. That will give you 19 newtons as well. That's the harder way to do it, and we've done that before, but since you already know the electric field, it's much easier just to use the definition of the electric field to find the force. All right, at what point is the electric field equal to 0? All right, well, we just sort of have to begin, although since we have charges of the same sign, I can imagine that the electric field is going to be 0 somewhere in between the two charges, because if I put my positive charge here, then it's going to be attracted to this charge and attracted to this charge, and those will have the potential to cancel out. But if I put my positive charge over here, it's going to feel forces in that direction. When I'm talking about my positive charge, of course, I'm talking about that imaginary test charge that I use to determine the direction of the electric field. So I'm going to put my imaginary test charge here in the middle. Now notice if I put it at C, it gets a field in that direction, but then a bigger field in that direction. And so that ain't going to be 0. So it has to be somewhere else. It's going to have to be farther away from the big charge. So it will be attracted to the minus 4q charge and attracted to the minus 2q charge in a way that they are equal. Because I'm further away from the bigger charge, that bigger charge imparts less of an electric field at that point, D. So the answer is D for number 11. Oh, you direct a beam of electrons between two charged plates in this figure. In what direction does the beam move? Very common way to move charged particles is to put them between two metal plates that are charged. In this case, imagine my electron comes in here. It's in between these two positive charges. It's going to be attracted to those charges and attracted to those charges so that the net force is going to be zero. So that beam of electrons is just going to go straight on through. And for that reason, then the direction of the electric field in the middle of the plates, there is no electric field in the very middle of the plates. In fact, if you were to really draw the electric field, it would sort of come out like this, something like that. But in the very middle of it, there would be no electric field at all. But we can see that thinking about the electron and what are the forces that are acting upon it in the middle of that, in the middle of those plates. So the beam is going to move to the right without deflection. There is no electric field in the middle of the plates. Consider this configuration of charges at the origin. Towards which quadrant does the net electric field vector point? Well, imagine my positive test charge there and ask ourselves what is the direction of the electric field or the force that acts on that positive test charge, and then that's the direction of the electric field. And let's try to draw these vectors with appropriate lengths. First of all, we'll take our biggest charge. It's going to feel a big electric field in that direction to the left. Due to the minus 4q, it will feel an electric field in that direction. Due to the minus 2q, a smaller electric field in that way. These two along the y-axis will add up like vectors, giving us a net vector that is smaller but still in the positive y direction. And so the resultant vector is going to be in quadrant 2. All right, Q1 has a magnitude of 10 coulombs. What is the charge of Q2? Well, Q1 is going to be plus 10 because the field lines are coming out of that charge. That means that Q2 has to be negative. So I'm left with B through E. Now, let's count the field lines. 1, 2, 3, 4, 5, 6, 7, 8 on this side, and 6 on this side. So my ratio of field lines is 8 to 6. That's going to be the same as the ratio of my charges. So 10 to Q2 is going to equal to 8 to 6. 60 divided by 8. If I solve this for Q2, I'm just looking at the ratios here, right? That the ratios of field lines are equal to the ratios of the charges. And so Q2 is equal to minus 7.5 coulombs. D is the right answer. We've seen this before, but it's been a little bit easier because we've had even numbered integer ratios, that the ratios have been an integer value, but in this case it's not, so you really have to go through this process of looking at the ratio. Which of these statements is true about charging by induction? Does not require contact. Metallic object holds a charge of this value. What total number of electrons? Well, minus 3.8 times 10 to the minus 6 coulombs, or microcoulombs. That's divided by 1.6 times 10 to the minus 19 coulombs. That's the fundamental unit of charge. On an electron, it has a negative value. You divide those two, and you get B, 2.4 times 10 to the 13 electrons. Shows 3 heavily charged plastic cubes. The net force on B is shown. Cube B has a negative charge. Which of these statements is true? Well, if it has a negative charge, the forces acting on it, well, the forces acting on it regardless of its charge have to be in this direction and in this direction in order to get this net force vector. That means that it's attracted to both A and C, so A and C both have to be positive, so 17 is C. This figures to two spheres. They initially have minus 2 and minus 1 coulombs, and then you have an interaction. They touched or whatever, or maybe there was a wire touched between them. The left sphere has plus 1 coulomb of charge. What is the charge on the right sphere? Well, look, I initially have minus 3 coulombs total, and that means I'm going to have to also have minus 3 coulombs over here. So this one has to be minus 4 coulombs, because when combining with a plus 1, so I get minus 4. What's happened here is I've had 3 coulombs of charge go from this over to here, minus 3 coulombs of electrons. Which of these is not an allowable charge? That's going to be this one. I can tell that because if I say 2.2 times 10 to the minus 19 divided by 1.6 times 10 to the minus 19, that's the fundamental unit of charge. Remember, charge is discrete. it is quantized, comes in discrete values, that is not an integer. It's something that's between 1 and 2. And all these others are integers when you do that. So 19 is B. Material is a conductor because, well, it's not that. It's not that. Conductors have neutrons. It's definitely not that. Protons do not move freely in a conductor. That's a true statement, D is, but that's not what makes a material a conductor, so E is the right answer. Two positive charges are a distance of 12 meters apart. A force acts upon them and moves them to 4 meters apart. By what factor has the potential energy changed? Well, potential energy, remember, is KQQ over R. So if I move them from 12 to 4 meters, that means that I've decreased this by a factor of 3. That means this has increased by a factor of 3. So 21 is B. Membrane walls are living cells of surprisingly large electric fields across them due to separation of ions. So, here's the wall of the cell. You got positive charges over here, negative charges over here. And so I have an electric field that goes across that membrane. What is the voltage then if you have this 5 nanometer thick membrane and electric field strength of 4 times 10 to the 6th volts per meter or newtons per coulomb? Those are the same units. So our voltage is equal to E times delta X. Actually, we had a little X subscript, I don't know if you recall that the voltage and the electric field are related in this way. It's our delta V. And so our change in potential across this electric field is going to be 4 times 10 to the 6 volts per meter times 5 nanometers, or 5 times 10 to the minus 9 meters. And that's going to be 20 times 10 to the minus 3, or 0.02 volts. This figure shows a map of equal potential lines. If you release a proton right here, which direction will it move? Well, what do protons do? I always like to go back to this figure. If I have a positive and a negative side, this is my high potential side, this is my low potential side. If I have a proton here, what direction is it going to move? Well, it's going to move in that direction. So it moves from high to low. So it's going to move towards a lower potential. All right, consider the previous figure. An electron initially at rest moves from a point equal potential line A to line C. What is the speed of the electron at C? Okay, so it's moving from A, an electron, to C. And by the way, that should give you some hint to the previous problem, that if electrons move from low to high, then protons move from high to low. So this electron experiences a potential difference of 20 volts. That's really what I want to see. It moves from 10 to 30 volts, so it has a delta V equal to 20 volts. It increases its potential by 20 volts. And I know that my change in energy is going to be Q times delta V. So that's going to be 1.6 times 10 to the minus 19 coulombs for my electron times 20 volts. And this is going to equal to 1/2 mv squared. All right, I know the mass. The mass is 9.11 times 10 to the minus 31 kilograms. And so I can solve this for V. And V turns out to be 2.7 million meters per second. So D. This diagram shows a collection of charges. At what point is the potential equal to 0? Well, let's see. At this point, potential is 0. These two cancel out. These two cancel out because I'm equidistant from opposite charges, and these two cancel out. Now, in a similar way, say at D, these two potentials cancel. These two, they cancel. It turns out if you go through all those points, you'll see that the potential for all of them is equal to 0. So all along this axis, the potential is equal to 0. Actually turns out, oh no, never mind. No, nothing, never mind. All right, so the volt is energy per charge. That's joule per coulomb. Electrons will tend to move. Well, gosh, let's see, we've already talked about this, but let's see. Plus, minus, this is high, this is low. If I have an electron here, what direction does it move? It's going to move from low to high potential. And then, let's see, what is your favorite topic to study? The Peloponnesian War, integration by parts. I don't think you'll do that in Calc 1. Mixed future tenses, maybe in your advanced grammar class. No, electric fields. Students sometimes find electric fields difficult, but I hope that hasn't been too hard for you.